the judges heavy like computational thinking valuable. Yeah.
Yes.
Yeah, we have like 300 people signed up for this. I think it's going to be in one of the huge, like the. That was funny. Yeah. I know it's going to be last. Yeah, that's a big one. And then we're hoping, to compete with it. Right?
No. Brick Hacks ended this month. RITDSE is next month.
Okay. Did you see the shared drive I put you on?
I haven't actually looked at it yet.
Okay, so just going forward with neural networks, feed forward, just basic examples and applications. So most of you have a vague idea of what neural networks are. They're essentially directed graphs, and they're set up to process data. Specifically with feed forward, the connections in a feed forward neural network only move from one layer to the next layer. You can't have connections that connect to a previous layer or back within the same layer itself. This is just an example that I pulled from one of my previous classes. The network does not need to be fully connected to count as feed forward. You can have missing connections, it's fine. Moving ahead, like you can even skip layers in the feed forward network. That is completely fine. The solid fact that you can't break is you can't have any connections that connect within the layer or that connect to previous layers. So for example, in this case, the orange connections and the green connections make this not a feed-forward network because these are RNN. It's a recurrent neural network, which we'll be talking about next week. We'll be getting more into the next week, but this is a recurrent neural network. The point is, because of the green and orange connections, this is not feed-forward because this is essentially a cyclic network. And feed-forward networks are acyclic always. Now just going over some basic activation functions because this is the first neural networks presentation. Every node, for example, like the input, the hidden 1, hidden 2, or hidden 3 nodes have an activation function. And these are functions that they execute on the incoming values to the node before pushing these values out the other end. These are the most common ones that are used. There's the identity function, which is you basically do nothing. You have the sigmoid function, which is another common math function, same with tanh. The ReLU functions or the ReLU functions are more specific to neural networks. The idea is you want to boost values that are greater than 0, but if it's less than 0, you want to limit them in some manner. The basic ReLU just has values less than 0 set to 0. The leaky ReLU doesn't set it to 0, but it severely limits it, so it's like 1/100th the previous value. And ReLU 6 sets a cap to prevent values from spiking as the neural network does its calculations.
How do you use some activation functions?
This depends on the data you're using, and specifically looking at it, some activation functions like ReLU 6 limits your upper value, and this prevents some weights from just skyrocketing when you're trying to balance the neural network. And it's ideal to prevent overfitting, and it sets limits to your neural network to prevent it from like.
Look at a lot of these functions, tanh like that. So there's like caps on the value, so it's linear.
Roughly, essentially, yes. I should have thrown up graphs. Would have been a bit easier to visualize. Now they're just going over how generally a neural network works in terms of weights and biases. Every edge connecting to nodes of a neural network has a weight, and generally every node has a bias going into that node. The bias value is a flat value that is just added to the value coming in from the edge before it is acted upon by the function within the node of the neural network. This is just how neural networks are set up. This is how they work. And this is a breakdown of how values within the nodes would be calculated with the assumption that all activation functions here are the identity function. It it's a basic calculation where you multiply the value coming into the edge by the weight of the edge, and then you add the bias value to that value as the input into your node. And it's just to break down how information is pushed down through the network. This is just a reference that I used, and going into the demo, it should be a bit easier.
What's actually being learned in the neural? What is it? What is the neural network learning?
So the neural network's trying to find patterns to identify which values correspond to specific inputs. And I've only explained the forward pass. Thanks for bringing that up. So once you get a value at the end, the neural network can identify whether the node that it lit up or the node that it shows as the final output was correct or not. And depending on the value it gets there, it pushes values backwards through the whole network in what's called the backward pass. And the calculations done through the backward pass are essentially working on derivatives of the whole network to essentially do what is gradient descent, to identify which direction the network needs to move, the weights need to move in the network to get to a more correct value and minimize loss. We don't worry about it too much here because we're using Python packages such as TensorFlow that take care of that for us, and that's seen more better in the demo. So yeah, just going over the demo as a whole. The most important package for us here is TensorFlow and NumPy. TensorFlow handles everything that you could ever want for a neural network for just basic execution in Python. Here, the dataset that we pulled is the fashion MNIST dataset. It's a basic existing dataset in TensorFlow. You can directly just call it from the Keras datasets. And while this is an image dataset, we are not doing any convolutions on it. We are basically going to be flattening the image into a one-dimensional array and using those values for it to carry out its classifications. Here it's basic. This is basic data preparation. We're splitting the data into a validation set and a training set, and we're splitting up the images and labels. This is an example visualization of how our data is. We're just plotting it out to see how the images exist and just identifying how they are. And this is like for a single example, and this is more showing the images as well as the classifications. And this is just like random data that's been pulled out from the data set. Now we're just preparing data for the neural network. We select a batch size for the neural network to work with. The batch size is how many entries or rows that the neural network will look at once before it tries updating its weights and biases to better fit the data. You can do it with a batch size of 1, where it'll be updating at each instance, but that is not ideal. You want to use a non-single batch size, and obviously you don't want to use the whole data set or your whole training example as a batch size either. This is just another hyperparameter that you can balance around to improve your network. Here, this is again just dividing the image values and casting it so it ends up as floating point numbers instead of just zeros or ones, which breaks your data. And we're just shuffling it around to prevent any possible hangovers from the initial part only being a specific class and then the middle being a specific class and so on. This is again more just setting up floating point values instead of integers, so your data isn't just zeros and ones. This is the most important part of setting up the network, essentially. We're setting up a sequential neural network here, so it has layers in order. The first layer is a flattened input of the image size. This would be of the size of your inputs normally. So let's say you have a data set that has 5 input parameters, this would be 5. It's just how we're setting it up. The second one we're seeing is a dense layer of 256. So we have 256 nodes in the second layer, and by saying it's dense, it just means it's connecting to all the previous nodes. The activation is a basic neural net ReLU. It's again a part of TensorFlow. You don't need to worry about this. It's just there. We have another dense hidden layer of 128 nodes. Again, because it's dense, it means it's fully connected to whatever's been behind it. Activation here is also ReLU. And our final output layer is again dense. So it's connected to all the previous 128 nodes behind it. And it's 10 here because we have 10 specific classes that the images are, we're trying to classify the images into one of 10 classes. And essentially with the way the neural network works is the output node that has the highest value is the class that is selected. So that's essentially how it makes its predictions when you're done with it. And this is a summary of how the neural network works. We have a flattened input of 784, which I believe is 28 by 28. Yeah, it's 22 by 22. Yeah, and then the first hidden layer is 256, second hidden layer is 128, and then the last layer is just 10. And essentially, even though this neural network is not that complex, there are about 235,000 trainable parameters that the neural network is going to train as it goes over our data and tries to define values. So you can select different optimizers for training the neural network. In this case, we've selected one called Adam. It is a commonly used one, and it is generally, unless you're getting into the specifics of what kind of optimizer you want to use, Adam works well in a general use case. This is defining our loss, and here we're using a cross entropy loss just to train the data better. This is a setup for training loss and accuracy. It is just basic metrics within TensorFlow itself. So we're not defining anything. We're pulling all these values from the TensorFlow package itself. This is going to be uploaded. You would essentially be able to use the same values and just change the data, and it will train fine. This is a training step. We're using gradient tape for defining the model. And essentially, when you run this whole for loop or function as a whole, it'll train over a number of epochs that you've defined. We've defined 50 epochs in this case. And each epoch is training one batch of data, essentially. So we defined a batch size as 128, and we have 50 here. So we'll be training what, 64, 6,400 data points, essentially.
Taking your batch and going through all the data once.
Wait, yeah, sorry, you're right. It's taking your batch and going through all the data once. Sorry. And after each epoch, the weights change, and you can see how the accuracy slowly improves as we change through our weights. And in the end, over 50 epochs, we end up with an accuracy of about 94.1%. You can run it for longer epochs, it just takes longer. And also keep in mind that it's not always better to keep running it for like 1,000 epochs. Eventually, you're going to hit a plateau where it doesn't really make that much of a difference. And you need to identify whether or not it's worth the payoff of having that many epochs compared to the computational time. This is just a plot of accuracy versus epochs and loss versus epochs. And eventually you'll identify that it is plateauing, as you can see. So that's up to you to decide when you want to stop. This is a random pull of the actual values of the image versus the predicted values. And just from the random pull, because we have about a 94% accuracy, most of these should just be the correct ones. You might have one or two incorrect ones. It's randomly pulled them, so I can't tell you which one's actually wrong or not, but yeah. than 301. Yep, there. So that's one example that's actually wrong. But generally, it predicts them pretty correctly based on the small neural network that's been set up. This will be posted again in the Discord, so you'll have access to the notebook and you'll be able to mess around with it. This is just applying some more pre-processing and seeing with some pre-processing if the loss and accuracy improves based on a single check. And this is after running it again, I think.
This is the test set.
This is test set. This should be the test set. Yeah. I'm sorry, I'm not the one who coded this. I got this about 2 hours back, so I'm just going to be upfront. But this all works. This is essentially how you can use TensorFlow to go through your data. You can use TensorFlow to set up a network in the way you want. If you go to, it's not what I need to do. Yeah, so basically like dense nets and whatnot are an example I just wanted to pull up where TensorFlow by itself, it is very well documented for Python, and they have predefined dense nets where you can just go in and plug your data into the dense nets and let TensorFlow train your data on those dense nets and generate a neural network for you to use.
Look at the dense layer document.
Yeah. It's tensor layer, right?
I think it's dense.
There's the dense.
And then it gives you all the parameters.
Yeah. So you can define your activation function. You can define an incoming bias. You can define any regularization you want to do on your data to make sure your data is within bounds or on the weights itself. Yeah. Is there anything else? Yeah.
Yeah, I have a question. From your experience, what do you think is the effect of having more layers?
Okay.
Is there
Yes.
better accuracy or more training time? Or what
So
is-
yes, adding more layers will add more training time, but it's not that significant unless you're adding like 4 or 5 more layers compared to what you already have. And it depends on your system as well. But generally adding more layers causes more parameters to exist that can be tweaked to make predictions. And that by default will improve your training accuracy. But
You don't want to make it too shallow.
Yeah.
You don't want to make it too deep.
because if it's
Magic.
if you have yes, so it's something you can mess around with to try and find a sweet spot that works for you. Because if you have like, let's say 100 layers, with each having a few hundred nodes, you have so many parameters that the network can train on that you end up overfitting on your data. So on your training data, you'll have wonderful accuracy, but on your testing data, it might not be that good. So you want to balance. So it's the whole bias variance balance you want to find. Grid search. Yeah, you could talk to Travis because that's what that is essentially what his research is in. But so the issue with, you could use grid search, but the issue with that is you probably need to use a grid search within a grid search because you don't just have layers, you have number of nodes within the layers and the number of connections that those nodes have to the previous and next layers. So you can assume to be using densely connected for everything, but that is not always what you want to do. In some cases, it's just better to not have some connections moving forward and train your network on that, and that works.
Problem is like neural network architecture search is an infinite dimensional problem because you can keep adding layers,
Yeah,
keep adding nodes.
You can keep adding layers, you can keep adding nodes, you can keep adding connections. So, and like in the example we've shown, we don't have connections that skip layers, but you can add connections that skip layers completely. And that changes everything essentially about your network.
Search can get out of hand on network. It's like, okay, you have number of layers you want times number of nodes you want to try times number of activation functions you want to try
Times edges.
Batch sizes you want to try times, like you get to like, okay, well now we need a grid search like 100 million.
Yeah, it goes exponential because just the number of hyperparameters you have that you can tweak and change are massive. So just finding a set that works for your data is often good enough. Like you can try tweaking it more, but generally with how neural networks train, it is not hard to hit over 95% accuracy. Generally.
Yeah, so
Yeah.
under the funnel and then you just narrow down.
Yes.
to 10 activities.
So
Is there any guide,
so the reason we have 10 at the end is we had 10 classes. So
is there a particular way or some general?
that see,
I know search is hard.
Find an architect that someone else uses.
yeah, no, so that is actually a very common thing that people do. You can find an existing architecture and just use that. I would say, personally, I would say start out with like 3 layers, and the number of nodes you split into depends on your input parameters as well. Like in our case here, if we look at how many input parameters we had, here we had like 784 input. So initially we have a massive amount of input parameters that we're cutting down and we're funneling down. It is possible that you want to expand initially if you don't have enough input parameters and then cut down, but the idea is you wanted to trend in the same case. Yes, look at what worked for others and then just adapt it to what works for you. Like if someone else had something that had like 5 inputs and then they made it 10, 15, and then they brought it down to 2 and it worked for them, you could try something similar and then tweak it as needed.
All the search algorithms are like a glorified or a smart way to guess and check. There's no like mathematical formulas involved.
Yeah.
Like what architecture.
If you find something, write a paper. If you find something, write a paper about it, get it published, and then just yeah. That's basically how it is, because you find something that worked in a similar field, apply it. If it doesn't work, unfortunately, try something else.
I feel like using a paper is like the way to go. It often does feel like.
Or you can use someone's pre-built like architecture.
Yeah, I mean, like we showed in the TensorFlow docs, they have pre-built dense nets for you to just use.
So we're gonna have a guest talk kind of after we go through all the neural networks about neural evolution, which is like a very smart way to do an architecture search. So you get one method to do that, but there's like grid search, you can random search, you can naive, there's just a ton of ways to do it.
Yeah. What rainforest is that the one you use? Rainforest merge.
Yeah, and if you actually look into the literature, it's like, well, since you have like an infinite dimensional space, it's probably like an infinite amount of like equally valid architectures for your problem.
So, like one of the ways you can do it is you essentially set up a rainforest of neural networks, and from the ones that perform well, you adapt characteristics and merge them together.
That's an evolutionary algorithm.
Yeah, that's an evolutionary algorithm, but
if you don't know something and you're like talking to people, important to say it's an active area of research. So that it's an active area of research.
Yes. So six,
Why did they cap at 6? Why 6?
I mean,
so six is another hyperparameter.
Oh.
So it is another thing you can tweak. You can have ReLU 10, you can have ReLU 3, ReLU 2. It is another one that is just a hyperparameter that's been used. 6 is a common one that Travis likes. So I'm going to stick with it because I trust his judgment. So that's basically why it's ReLU 6.
just put, value cap the linear part of the granular.
Yeah. So you can find something that works better for you, like ReLU 11 might work great, but it's just something else. Any other questions or? No. Anything else you wanted to talk about, Lee?
No, I'll keep for next week. We go to recurrent nets.
Okay. Let me just close this up then.